And is the first thing you guys did focus on the factorials? I mean, not the factorials. The first thing that I would focus on is I would focus on my actual derivatives. I would look at my derivatives first. So we want the summation k equals 0 to infinity. The kth derivative, 0 over 0 factorial times x minus times k factorial over x minus 0 to the kth power. So at first, and as you're doing your homework, many of you guys have already done a lot of the homework. As you're doing your homework, you're looking for patterns to develop. When you go to write your sigma notation at the end, you're looking for these patterns to develop. Were you guys able to come up with like a summation formula? What'd you put here, Drew?
I put 3 to the n times x to the n over n factorial.
Beautiful, beautiful. Is that what you guys all got? So 3 to the n, x to the n factorial. Very nice. So that is a way to describe that infinite summation that develops with the Taylor series. And then we want to take that pattern and we want to find the interval of convergence and radius of convergence. And to do that, what did you do? Take the
I did the ratio test.
Ratio test. Very nice. So the ratio test will help us get, I'll just put down the ratio test is a way to work this through to get the interval of convergence. And so doing that ratio test, we take the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 factorial times x to the n plus 1 divided by 3 to the n over n factorial times x to the n. And then things canceled out. Let's see what happens. As n goes to infinity, we have 3 to the n times 3 to the 1 times x to the n times x to the 1 over n plus 1 times n minus 1 dot dot dot. And then n factorial times 3 to the n, x to the n. And so let's see what cancels up here. And remember, we can separate that x part and even pull it out if you want to, and just focus on taking a limit as n goes to infinity of the rest of it. That whole thing, thank you, James, that whole thing goes to 0. So that means the absolute value of any number times 0 also is 0, which is always less than 1. And when you apply the ratio test and you get a number that's always less than 1, that means this always converges absolutely. So you would say that your interval of convergence is negative infinity to positive infinity, and your radius is also going to be infinity. But I'm going to stop. How's that warm up? How excuse me. So I'm just going to throw a bunch of these up here for us to see if you guys are matching. Excuse me again. Ay, ay, ay. Do you see?
Yeah.
Okay. Same thing will happen on the bottom as well. Yes. How are you? You're writing down some terms? Yeah, nice. So now you notice the only terms you have are evens. Nice, you did it. Very good. So now use the ratio test. Very close. So sine of pi is 0. I get that this drops out. I think, you see what I'm saying here? And I think your first term will be a negative 1. Yes, you got it. Yep. That'll be a negative 1 here. And that's a 0. And that's a 1. Yes, it'll be n plus 1. I agree. And the bottom and the power should be 2n, I think, because you're hitting all the evens only. Yes. Correct. When you're doing the ratio test, the absolute value of negative 1 becomes negligent. You don't need it at all.
So wait a second.
2 factorial. Correct. You got it? Ah, good. So the odds drop out, and you're only left with evens. And so to get just even up here, you want a 2n, and that's correct. Yep, and the 2n on the bottom is good. Get rid of that part. Yeah. And no x's. You don't need the x because you have it with the pi. You see how you have it? And then, now you're perfect. Let's see. So when you go to write out your series, it looks like you have a -1 on top, and then a 0 factorial, and then an x minus pi to the 0th. And then a 0 on top over 1 factorial, x minus pi to the 1, and then a 1 on top, 2 factorial, x minus pi to the 2, and then a 0 on top, 3 factorial, x minus pi to the 3, and then a -1 on top, 4 factorial, x minus pi to the 4, and then a 0 on top, 5 factorial, x minus pi to the 5, and it goes on. And so what happens is, and I see everybody's working these through, all your odd powers go away, and you're left with just even powers. A -1 over 0 factorial times x minus pi to the 0, plus a +1 over 2 factorial, x minus pi to the 2, minus a 1 over 4 factorial, x minus pi to the 4, plus ... And you're getting just even powers. So because our powers are just evens, we're going to describe that as the sequence 2n. 2n's give us just our evens, 0, 2, 4, 6, 8, starting when n is 0. No, yes. So, let's see. So I can rewrite this sum n equals 0 to infinity. And I looked, everybody seems to have this. You have on the bottom the evens, factorial. You have as your power the evens. And the only piece left is to figure out the -1. But you need to make sure that your first term is negative and the next term is positive. When n is 0, you get a negative. When n is 1, you get a positive. And the only way for that to happen when you're oscillating is to put a +1 up there on that -1. So everybody should match me when it comes to expressing their power series. It should be -1 to the n plus 1 times x minus pi to the 2n over 2n factorial. And from there, you can find your interval of convergence by using the ratio test. And you have to be really careful with this one. When you go to put the -1 inside, you can actually ignore it because the absolute value of -1 is just 1. So you really can ignore it, but I'll just write it there so that we have it. The next guy is x minus pi to the 2 times n plus 1. And I want to highlight that right there. It's 2 times n plus 1, which is really 2n plus 2. So that power on top is a little different because we have these evens going on. The same thing happens down here in the denominator when you do this factorial. You have a 2 times n plus 1. So that guy as well is 2n plus 2. And that's going to get divided by -1 to the n plus 1. But we just said the absolute value of a negative or a positive will just be 1. And then x minus pi to the 2n. And then 2n factorial. So let me write out what that is. That's the limit as n goes to infinity of, on top, I have x minus pi squared, x minus pi to the 2. And when I flip and multiply, I have 2n times 2n minus 1, dot, 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 dot. On the bottom, if I expand out my 2n factorial, I have 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, dot, dot, dot. And when I flip and multiply the bottom, I have x minus pi to the 2n. And let's see if you guys are getting the same thing I am. Oh, whoops. I didn't put the n on here. He cancels. He cancels. So it looks to me but this limit again goes to 0, and 0 times any quantity, well, is going to be 0. And so that means I have always a string of 0 is less than infinity. That means this thing always converges absolutely. And so again, the interval of convergence is negative infinity to positive infinity, and my radius is infinity. And the implications of this are phenomenal, right? It means we can take a cosine function, rewrite it as an infinite polynomial right here, express it as an infinite polynomial, and it will always, for the entire interval, converge, meaning they will be identical. Those functions will converge to be the same thing. With the function, and then we take our first derivative, which is 1 over 3x minus 2 times 3, which I'm going to rewrite as 3x minus 2 to the negative 1 times 3. And then we take our second derivative, and I'll focus over here. So it's the derivative of this guy, which is going to become negative 1 times 3x minus 2 to the negative 2 times derivative of the inside. 3 times, I already had a 3. Third derivative is negative 1 times negative 2 times 3x minus 2 to the negative 3. Derivative of the inside, but now take what I already had last time. Fourth derivative is negative 1 times negative 2 times negative 3. 3x minus 2 to the negative 4. 3 times, and now I had these guys already. So there's a pattern. There's an absolute pattern that's developing. And like you guys said, it's a factorial. We've got a factorial coming on here. So we've got some patterns going, but remember your next step is to now take and plug in 1. So you want to take f of 1, f prime of 1, f double prime of 1, f triple prime of 1. I'm going to come wander. What do those coefficients, what pattern is erupting? So, John, let me ask you first. Do you see how the first term's a 1, and then it goes negative 1, and then it's 1, and then it's negative 1, then it's 1, right? Yeah. So we've got a negative 1, now either to the n or n plus 1. So if I let it be n, and I put 1 in for n, that just gives me a -1. Do I want a -1 on this first term? So n plus 1 up here, right? I need an n plus 1 up here. Now we also know we've got powers of 3's, right? In fact, I think it's 3 to the n. Oh, and there's more that has to go in there. So let me erase this back end part. So I've got a -1 to the n plus 1. I've got a 3 to the n. On the back side, I've got x minus 1 to the n over n factorial. And right in here, I have one more piece, which is these 1 times 2 times 3, 3 times 4. You guys are telling me it's a factorial. In fact, how am I going to express that? N minus 1 factorial. It is. It's one less, isn't it? It's one less. So that when I'm at my 5th power, I'm only going to 4 factorial. When I'm at my 4th power, I'm only going to 3 factorial. Exactly. N minus 1. Let me see if we can clean that up a little bit. So that means we're at n equals 1 to infinity, -1 to the n plus 1 times 3 to the n. I've got n minus 1 factorial, which is n minus 1 times n minus 2 dot, dot, dot. And then I have n factorial, which is n times n minus 1 times n minus 2 dot, dot, dot. So I can do one more thing to clean this up and make this nice. This one is really tricky. This one is really tricky. -1 to the n plus 1, 3 to the n, over just n, times x minus 1 to the n. See if you're getting the same thing I'm getting. Is that what you guys are getting on that?
Will you just skip the first term to 0 for when we're doing making our...
I am. Now, if we want, we can plug in n equals 0. You could do that, but the problem is then I'd have to be really careful, because if n is 0, that gives me a 0 in the denominator. Do you see? When things cancel. So I think I want to start mine at 1, unless we change and make like that bottom term n plus 1 and then start at 0. So I'm not sure how WebWork wants you to. I would define it just like this and skip that first term. If they're making you start, then you want, if this is going to be n equals 0, then you just have to up everything by 1, I think. I think you just have to up everything by 1. But I like this guide. I like this definition better. It's nice and sweet, much simpler to work with. But once you get that down, make sure you got that and you see how all those factorials cancel. It's really clean. It's really elegant. But now you want to apply the ratio test to this to find our interval of convergence, okay? Apply our ratio test. You guys are so good. It took us probably, I'd say, half hour last class to figure this out. It took us a really long time to go through this. I'm going to come around and see and make sure everybody's on track. This one is tricky. And be sure, guys, to check your endpoints, okay? Because remember, to find our intervals of convergence, if it's a finite interval, you want to check your endpoints as you go. At the very end, after you get everything done.
did you get n plus 2?
I took n plus 1 plus 1, right? In place, to get your a sub n plus 1 term, you're going to substitute n plus 1 everywhere you see an n. So that would become 3 to the n plus 1 plus 1, which is 3 to the n plus 2. And I skipped a step, and then I put 3 to the...
n plus 2 on the bottom.
Ah, so on the bottom, did you have n plus 1? Oh, I messed that up. Oh, thank you. I messed that up. Oh, that's my bad. I started using the wrong one. My bad. Oh my God, I did the whole thing wrong. But luckily, it wouldn't matter. But okay, I was using the wrong one, wasn't I? Thank you. I was using the second definition, which you could do because either one is the same definition. They just start at different places, and it doesn't matter because we're looking at our endpoints. Ignore what I just did. Let's make it simpler. Let's focus on the star guy. Okay, so I want to do negative 1 to the n plus 2 times 3 to the n plus 1 times x minus 1 to the n plus 1 over n plus 1 times, thank you, Max, thanks, over 3 to the n times negative 1 to the n plus 1 times x minus 1 to the n. Okay, now let's see. That goes away. Those are absolute value of negative ones go away. That goes away. So that is giving me 3 times, undo, erase this. So that's giving me equals the limit as n goes to infinity of 3n over n plus 1 times the absolute value of x minus 1. The limit as n goes to infinity of 3n over n plus 1. That just goes to like infinity over infinity. So we could use L'Hopital's rule if we wanted to, or we could just look at the highest power on top and the highest power on bottom. And so you guys will see that that goes to 3. So this is 3 times the absolute value of x minus 1, and you want that less than 1. And that's how you're getting your interval, right? So that's going to be absolute value of x minus 1 is less than 1/3. Negative 1/3 is less than x minus 1 is less than positive 1/3. And then you're adding 1 to all the sides. Plus 1, plus 1. So I'm getting so far an interval from 2/3 to 4/3. But then you have to check your endpoints, okay? Check your endpoints because this interval is a finite interval. So you're going to need to check what happens at 2/3, what happens at 4/3. So at 2/3. But I'm going to stop and walk and make sure. So that gives us negative 1 to the n plus 1 times 3 to the n over n times. And x minus 1 becomes 2/3 minus 1 to the nth power. Now what is that really? That is really negative 1 to the n plus 1 alternating 3 to the n over n. This is going to give us 2/3 minus 1, which is negative 1/3 to the n. And so I can combine I'll keep my alternating out front, but I can combine that 3 to the n and the negative 1/3 to the n to get negative 3 over 3 to the n. Oh my goodness. So what's that give me? Negative 1 to the n times a negative 1 times a negative 1 to the n over n. Now these guys are both in n, so I can multiply them and get positive 1 to the n for that piece. So those guys are just 1 to the n. So it looks like it's leaving me with what's that? What is that, guys? That's your what? That's just, let's pull out that negative 1 because that's a constant. It doesn't have an n on it. So I can pull him out front. What is that? That's the what? That's the harmonic series. And what does the harmonic series do? It diverges. So that part diverges. So that means that 2/3 has to stay open because we're diverging. Well, if you guys did enough homework, you're going to find the opposite happens on the other side, right? If we do the opposite, we should get that it converges because I'll put negative 1 to the n plus 1, 3 to the n over n. This time I'm putting in 4/3 minus 1. And so I think this time what happens is I have negative 1 to the infinity. I have negative 1 to the n plus 1. I have 3 to the n times 1/3 to the n all over n. And those two go together because they both have n powers. So that's just n equals 1 to infinity of negative 1 to the n plus 1 times 3 over 3 to the n. That's just 1. And so that's just giving me n equals 1 to infinity, the alternating series, negative 1 to the n plus 1 over n. That guy's our alternating harmonic, right? And what does the alternating harmonic series do? He converges. And so that means that you're going to have to continue and put a closed bracket up here for that interval of convergence. So your interval of convergence is open at the left endpoint, closed at the right endpoint. And if I want to get my radius, what do I need to do? I need to take the length of the whole thing and divide it by 2. Yep. So the radius is 1/3. Oh my goodness. That took a long time. That was a doozy. How are you guys? Does anybody have a question?
Yeah, actually.
Yes.
So when you're like, if you just look at it,
Mm-hmm.
like, couldn't you put this down there?
Yes.
3 to
Yes, you can. Yes, you can. Yes, you can. Yep, 1,000%. But then you have the negative 1 to the end that stays with it. Yes, you can. 1,000%. Absolutely. Absolutely. Other questions? Other questions? How's everybody? You doing okay? Any questions? There's one more piece that might trip you up on your homework. So I want to pull in one more problem for us to work. But I want to make sure everybody's okay first. How are yous? So let me pull in a problem. Let me see if I can pull in. Oh, okay, not that. Not that, but I can't do that. Undo. Nope. Add a picture. First thing I want to show you is this right here. When you're taking your Taylor series, if we stop it at a certain point, for instance, if we stop it right here when our power is 2, we call this the second degree Taylor polynomial. If we take our Taylor series and stop at 3, we call that the third degree Taylor polynomial. So remember, the Taylor series creates this infinite polynomial, but we can approximate functions by stopping or truncating this polynomial that goes forever and ever. And if we stop or truncate it, that becomes what we call the nth degree polynomial. So the first degree, the second degree, the third degree, the fourth degree polynomial. And from that, we can use that idea to generate more things. Namely, what that allows us to do is the Taylor polynomial will allow us, without a calculator, to approximate things. F of a certain number. It allows us to approximate it with polynomial. So let's get an example. Okay.